All right, let's get into it. We're about to go on a pretty wild ride, starting with a sound you hear all the time, and ending with the very fabric of time and space itself.
So it all kicks off with a really simple question. Have you ever noticed how the siren on a passing ambulance seems to change pitch? You know that classic neo sound as it rushes past?
Well, that familiar change in sound actually has a name. It's called the Doppler effect, and it tells us something really fundamental about how waves work when things are on the move.
To put it simply, when the thing making the wave is moving toward you, those waves get all bunched up, and when it's moving away, they get spread out. It's kind of like if someone was running towards you while throwing baseballs, you'd catch them a lot more often, right? So imagine a sound source that's just sitting still. It's sending out sound waves perfectly evenly in every direction. Think of the ripples in a pond when you toss a rock in. The spacing is perfect, the frequency is the same for anyone listening, no matter where they are. But the second it starts to move, everything changes. Look at how the waves in front get squished together. See, each new wave is sent out from a position that's a little bit closer to you. That compression is what jacks up the frequency, and that's the high pitch you hear as the ambulance gets closer. And behind it, the exact opposite happens. The waves get stretched out, which lowers the pitch. Okay, now let's crank it up a notch. What if that source is moving at the exact speed of sound? Well, it basically keeps catching up to its own sound waves. They can't get away, so they just pile up, one on top of the other, into this massive wall of air pressure. And when that wall hits you, you get a sonic boom. And if it goes supersonic, faster than sound, it's actually outrunning its own noise. The waves that would normally be in front of it get left behind, forming this cone-shaped shockwave. So the jet will fly right over you in total silence, and then, boom, the shockwave finally catches up. But here's where things get really, really interesting. This whole principle doesn't just work for sound. It turns out it's the key that unlocks one of the biggest, most mind-bending ideas in all of physics. You see, the exact same thing happens with light waves. When we look out into the cosmos at distant galaxies, we can see they're moving away from us because their light gets stretched out. This stretching shifts the light towards the red end of the spectrum, and astronomers call that redshift. It's one of the biggest pieces of evidence we have that the universe is expanding. Now, thinking about all this led Einstein to a truly revolutionary idea. He thought, what if for things moving incredibly fast, it's not just the waves that get stretched? What if time itself actually slows down? This is a phenomenon we now call time dilation, and it completely rewrites the rules of reality as we know it. To really wrap your head around this bizarre concept, physicists came up with a famous thought experiment. It's known as the twin paradox. Okay, here's the setup. You've got two identical twins. One of them becomes an astronaut and blasts off into space on a super fast trip to a nearby star and back. The other twin? They just stay at home, here on Earth. So, according to everyone back at Mission Control, watching the spaceship's clock from Earth, the entire round trip is going to take exactly 10 years. The twin who stayed home will be 10 years older when their sibling finally gets back. Simple enough, right? But here's the kicker. For the twin who was traveling at 80% the speed of light, time itself was moving slower. So when they step out of that spaceship, they will have only aged 6 years. They are now literally 4 years younger than their own identical twin. This is where the paradox comes in. Because from the perspective of the twin on the spaceship, Earth was the thing moving away at high speed and then coming back. So shouldn't the twin on Earth be the one who's younger? Both of them think the other person's clock is the one that slowed down. It seems like a total contradiction. So how do we solve this? Well, the answer isn't about who was moving, but about how they moved. It turns out their two journeys were not symmetrical at all. And that little detail is the key to unlocking the whole thing. The real insight here is that their paths through the universe, through what physicists call spacetime, were fundamentally different. See, one twin just coasted along on Earth, while the other had to accelerate like crazy, turn around in deep space, and then decelerate to come home. And this diagram shows it perfectly. This is a space-time diagram. The twin on Earth travels on a nice, straight line through time. But the astronaut's path has this big kink in it where they had to turn around. And because of the weird geometry of spacetime, that bent path is actually shorter in terms of the time they experienced. It was the acceleration, that change in motion, that broke the symmetry and made the spacefaring twin age less. Now, I know what you're thinking. This is all just a cool, bizarre thought experiment, right? Well, not exactly. We've actually designed and launched real-world missions to test these strange effects of spacetime.
And this is it. Meet Gravity Probe B. Back in 2004, NASA launched this incredibly sophisticated satellite. Its mission was one of the most ambitious ever attempted, to measure, with insane precision, exactly how the mass of our planet Earth warps the space-time around it. The probe spent over a year just meticulously gathering data. Then it took scientists years of incredibly careful analysis to filter out all the noise and pull out the almost impossibly tiny signals they were looking for. So after all that time, all that effort, what did this incredible experiment find? Was Einstein actually right about our warped reality? The results were, and I mean this, a stunning confirmation. The probe measured two different effects that Einstein's theory of general relativity predicted. The first, the geodetic effect, is basically the way Earth's mass creates a little dip in spacetime. The second, frame dragging, is how Earth's rotation literally twists spacetime around with it, like a bowling ball spinning in honey. And as you can see, the measurements matched Einstein's predictions almost perfectly. It was an incredible achievement.
So there you have it. We went from the simple sound of a siren to a mind-bending paradox about twins, all the way to a real-life space mission. And what they all show us is that our everyday view of reality is just a tiny sliver of a much stranger, much more flexible universe, one where reality itself is literally shaped by motion. And that leaves us with one final, pretty provocative thought to chew on. If something as basic as the flow of time actually depends on how you're moving, what does that say about the nature of reality itself? What is truly real?